Okay, let's go to our quiz review. All right, guys, let me get your attention. All right, let's look at number one.
You're gonna ask him. You're gonna ask him something.
So, yes. Okay, so we have our velocity graph showing moving along the coordinate line in meters per second. It says when does the particle reverse direction? So we know that if this is our velocity function, then anything above the axis is going to represent positive velocity. Anything below is negative velocity. Anything on the axis is going to be where your velocity is zero. So that means here, positive velocity maybe is speeding up, and then but still moving to the right, and then eventually is going to stop, turn around, move left, speed up in the negative direction, and then slows down, stops again, and then moves to the right again. Right. So that's the outline of the movement for this particle. So part A, when is the body reverse direction? Yeah, t equals 4 and t equals 8 because velocity changes signs. When is this particle moving at a constant speed? Yeah, 67, right? It's holding steady at -3, velocity of -3 meters per second. And then what is the maximum speed? 3 meters per second, right? Either up here, but it's also down here as well. These are both moving at 3 meters per second. And at what time is the body slowing down?
2 to 4.
Yeah, 2 to 4. Here he's moving to the right, but then he's slowing down. And here he's moving to the left, but then he's slowing down as well. And also, you can also think of it as, when the signs are opposite between velocity and acceleration, right? So here, my velocity is positive, but my acceleration, which is the slope of velocity, is negative. Here, slope of velocity is positive, but my velocity is negative below the x-axis. Okay, any questions with first part?
You have to always have explanations.
If I specify. If I don't, then you don't have to. All right, so number 2 through 4, 2 and 3 says use L'Hopital's rule when possible. So try 2 and 3, but number 4 is asking about the derivative. So we're not going to do L'Hopital's rule for number 4, right? Okay. Yeah. Okay. Let's see.
Test different instances and put them on test. Let's get thanks.
Okay, so number 2, direct substitution gives us 0 over 0. That gives us the green light to do L'Hopital's rule. numerator is 1, denominator is 2x minus 7. We reevaluate, we get negative 1/3. That's our limit. Number 3, direct substitution gives us 0 over 0, L'Hopital's rule. 6x over e to the x minus 1. We get 0 over 0 again. So we do L'Hopital's rule a second time. 6x becomes 6, e to the x minus 1 becomes e to the x. Direct substitution, we get 6 over 1, which is 6. Number 4, it's asking for you to find the derivative of that expression, so we have to go through quotient rule there. So number 4 is there just as a reminder that L'Hopital's rule is not a replacement for quotient rule. It depends on what you're asked. Either you find the limit or are asking to find the derivative.
Use it everywhere else unless it's quotient. Oh,
Say it again.
you can use it anywhere else.
What's it?
No,
L'Hopital's rule. You can do L'Hopital's rule as long as you get 0 over 0 or infinity over infinity, but it's always within the limit context. So we don't do L'Hopital's rule unless it's a limit problem.
I need derivative.
No, derivative, we never do L'Hopital's. Right. If you look at number 2 and 3, these are asking about the limit of an expression. Yeah, L'Hopital's rule is only for something involving with limits. If it's asking for derivative, then we have to use our derivative rules. Okay, let's look at number 5. I'll do this with you. Okay, it says if the length of a rectangle L is decreasing at a rate of 2 inches per minute, while its width is increasing at a rate of 2 inches per minute, which of the following must be true about the area of the rectangle? So we know the length is changing, the width is changing as time is passing. So anytime we see something in relation to time, we always want to consider, wait, this is maybe a related rates problem. So we start off with the area formula for a rectangle, which is length times width. We want to find the derivative so that we can get dA dt and dL dt and dW dt to show up. So we got to go through our derivative process. The right side, though, we have to go through product rule because these are two different variables being multiplied with each other. Okay, so f prime g plus f g prime. The length is decreasing at a rate of 2 inches per minute. What can we assign this to be? -2 for what? dL dt. And then 2 inches per minute, width is increasing. What can we say? dW dt is +2. So if I factor the 2 out, I can get same thing as 2L minus 2W. So now if we have this in front of us, we can kind of go down the list and see which one is going to make sense. A is always increasing. Well, that means dA dt is always positive, which may not be true because if W is greater than L, then we're going to get a negative dA dt, and that would cancel this possibility out. A is always decreasing. That's not always true either, because if L is greater than W, then my dA dt is positive, and A is decreasing would be dA dt negative, and that's not always true. A is increasing only when L is greater than W. True or false? This is true, right? If L is greater than W, that will guarantee this is positive. 2 times positive is still positive. dA dt is always positive. So this is the one that fits. This problem was taken from a old AP exam, so that's interesting to see it that way. Hey, do we do all of page 6 together? Oh. All of it. Okay. All right, let's see if we can finish it up. Which part did we get to? All right, okay. Okay, is velocity increasing or decreasing? What do we look at? This is talking about the slope. Yeah, this is talking about the slope of velocity. So increase, decrease. It wants to know, is velocity looking like this? Or is it like this? And if it's talking about the slope of velocity, then we just look at acceleration. So we let A of 2 decide that for us. So since acceleration is a positive 6, velocity is increasing. But for J, is speed increasing or decreasing? What do we need to do there? Yeah, compare velocity and acceleration. If one is positive, the other is negative, speed is decreasing. But if they're both the same signs, if they're both positive, or if they're both negative, then speed is increasing. And then for part K, find the average acceleration. How do you think we define average acceleration? It's similar to average velocity. Average velocity, we don't use velocity, we use the function above it, right? Change in position over change in time. So therefore, average acceleration can be defined as what? Change in velocity over change in time, yeah.
The displacement from a part from these.
We just do final position minus initial position, yeah. Use position, yeah. Change in position divided by the change in time. Okay, next page, number 7. Number 7 says the function is concave up at, oh, sorry. Yeah, sorry, not question mark there. The function is concave up at x equals pi over 6. What is the estimate for f of 0.5 using local linear approximation? So for number 7, we first want to build our tangent line equation. So let's gather our order pairs. So plug pi over 6 into the function to get your x and y value. And then we need to find the derivative. Find the slope. The slope comes from the derivative. So we got to go through a little bit of chain rule to build the derivative. From the derivative, you can plug in to find your slope. do your point slope form, and then at the end, you can plug in the 0.5 in for the x to get to your linear approximation. Okay, let's try those steps.
Why would we use a calculator?
Yeah, you can use your calculator anywhere. I think if I'm some of these I'm looking for exact values though, so I do want you to gather these unit circle values, and then at the end you can leave your answer unsimplified. So you technically don't need a calculator for this, but you can for other parts. I think it's mainly for the particle motion where some of the values can be a little messy in terms of plugging it. Right. Okay, so order pair comes from the original function. Plug pi over 6 into the x value of my function. I'm able to get it all the way down to 1 minus 1/2, which is 1/2. 1/2 squared is 1/4. Next up, I want to find the slope. The slope comes from the derivative. To get to the derivative, I have an inside-outside portion. I got to go through chain rule. Outside's derivative times inside's derivative. Go through and using unit circle values, get it all the way down to your slope value. Once you have your order pair and your slope, point slope form. And then from here, you can just plug 0.5 into the x of your linear equation. On the AP exam, if you leave your answer unsimplified, they will give you full credit. So this is perfectly acceptable as well. Next part, since the graph is concave up, we know that any linear approximation is going to sit below the curve. So any point on this line is going to be an underestimation of the actual point on the curve. Okay, any questions with 7? Okay, number 8, we have a cylinder barrel. So we know that anything that's cylinder should be, yes.
Sorry, I just for part B of number 7, you have to say f of x, at x equals pi over 6.
Well, everything is already at pi over 6, so the assumption is that it's at pi over 6. That should be okay, because this whole problem is centered at pi over 6, so we don't have to specify pi over 6.
Okay.
Cylinders, we know cylinders is easier than cones because typically these problems, the radius is never changing. So if I can figure out the numeric value for radius, I can just put it into the equation, and that should allow me to move into my derivative stage without having to go through a whole messy process of similar triangles. Okay. All right, so let's look at number 8. All right, a cylindrical barrel with a diameter of 2 feet contains collected rainwater. The water drains out through a valve, which is not shown at the bottom of the barrel. The rate of change of height is modeled by dHdt equals -1/10 root h. Find the rate of change of the volume of water. So we're looking for dVdt when the height of the water is 4 feet. Indicate the units of measure. So we know our formula for cylinder is V equals pi r squared h. Okay, we're looking for dVdt. But we should be able to find an easy replacement for radius, right? What's the radius that's never changing? 1. So I'll just rewrite the equation. And we should be able to move into our derivative process a lot faster than if we're working with cones. So V becomes dVdt. Pi h becomes pi dHdt. Make our substitutions. dHdt is -1/10 root h. Now that we have our derivative, we can look to plug in values. We know that this is a moment in time when h is 4. So root 4 over 10 is the same thing as 2 over 10, which is the same thing as 1 over 5. So negative pi over 5. Our units of measure, volume is in terms of cubic feet. Time is seconds. So cubic feet per second. All right, any questions with part A? Okay, part B, when the height of water is 3 feet, so we have a different h value here, is the rate of change of the height of water with respect to time increasing or decreasing? Is the rate increasing or decreasing? What is this referring to, you think?
The
Second derivative. Okay, rate of change is at the derivative level. Increasing on that is talking about the slope of your rate, which is basically the second derivative. So we have to find the rate of change of, so we know what dHdt was. We have to find the second derivative of dHdt, or second derivative of h. So let me clean this up here. Let me get this ready for our derivative process. I do want to do power rule on the right side. So derivative d2h over dt2. This is basically, yeah. We do power rule here. So bring down the 1/2. I get -2/10. Sorry, -1/20. H to the -1/2. Now I just took h's derivative, so what else do I need? The hdt. So this is my second derivative expression. To make it a little bit easier for me to interpret, I can replace this dHdt with what? Yeah, so there's my, that way I can kind of make my conclusion a little bit easier if I have everything in terms of h here. All right, if I clean this up, what happens? Root h is canceled out. I'm just left with positive 1/200, right? So if my second derivative value is positive 1/200, that means my rate is increasing because my second derivative is positive. Yeah, the rate of change of height of water is increasing since d2h over dt2 is greater than 0.
So like writing that you when you get your like 1/200, you put an arrow and like put a positive sign and then put another arrow so increasing.
What do you mean?
When you get 1/200,
Mm-hmm.
you just put an arrow and then like write a positive, like a plus sign, and another arrow and then say increasing. It's like show that.
Could be. Let me see what that looks like. Let's just write it down. I would say greater than 0. I think that's a little bit cleaner. I mean, I would know what you mean, but I'm just concerned that the greater than minus.
With college or maybe not with college of this.
That would be.
Okay.
I would say greater than 0. I think that's better. Okay, let's go to fine. This is a Pythagorean theorem problem. Okay, so here's our diagram. Person X and person Y are walking on straight streets that meet at right angles. Y travels south and approaches the intersection. Person X travels east and moves away from the intersection. Find the rate at which distance between X and Y are changing at these moments in time. Okay, Pythagorean theorem. Okay, so just filling in some values here. Y is 10 meters. Y travels south, approaches the intersection. So not because it's moving south, but because of the fact that this vertical component is shrinking. So that's why we want that to be a negative rate. Person X travels east. It's not because it's traveling east that's causing us to make it positive, but because we know that this length is growing over time. So we want that dx/dt rate to be a positive one. X is 20. So we can solve for z using Pythagorean theorem. A squared plus b squared equals c squared. And the rest can just all get plugged in to find dz/dt. Just so happens that at this moment in time, that dz/dt ends up being 0 meters per second. But if it was any other time, that rate of change will probably be increasing. Or yeah, so, but it just so happens at this moment in time, it just works out in a way where dz/dt is 0.
Sure. This unit is just a quiz, right?
As a quiz, yeah.
Wait for you to test that.
Yeah, we're gonna move into unit 5 after this. We'll finish parts B and C tomorrow. So B is involving finding d theta dt, and then part C is involving finding area. So if you look at the bottom of the page, these are what we're responsible for in preparation for Monday's quiz. So be able to tackle Pythagorean theorem problems, which we just got done doing. Area of a triangle, we're going to see that for part C, where we got to go through the product rule. Sphere, I'll give you those formulas, but dv dt, ds dt, trig related rates, we're going to do that for part B that we didn't finish today. Cone problems, where you got to do similar triangles. Cylinder problems, where you want to replace the r so that becomes easy with a derivative. Shadow problems, where you got to do small height is a big height, as small base is a big base, and then be able to interpret dx dt, dy dt, and then the rate of change of the tip of the shadow. And then the formulas that you're expected to memorize are Pythagorean theorem, area and circumference of a circle, area of a square, area of a triangle, okay, and know your unit circle. So tomorrow we'll start our next unit, but I'll come back, we'll finish some of these, and then on Monday, we'll just pick out problems from the packet that I gave you, just for extra practice relating to one of these types of problems. Yeah.
Quick question. When do we expect to have our test?
Yeah, sorry, it's a really busy week. I'm about quarter of the way through. I hope, yeah, I'll definitely have it done by the weekend and in the grade book by this weekend.
Okay, thank you.
All right, guys, come get your phones. No, so you see how your review packet is pretty thick? I just included a bunch of A/B reviews, so I think anything that you want to find relating to these, you can find there. So I'll just pick out those problems for Monday. Yeah.
Right. I can get my. Where's it? In the line.